Anybody?
Okay, I'm not. All right.
All right, okay, I'll get out of your way.
Hi, Jen.
Just make sure you stay kind of close to the computer when you talk.
Yeah.
It's recording?
Yeah, I don't know if we're sharing our screen though. Are we?
Yeah, make sure.
Oh, we are. Okay. Cool.
Yeah, or you are screen sharing and recording.
Cool, cool, cool.
I'll be back.
Okay, hi everyone. Hello. Hi. Cool. So me and Emily are going to be giving today's lecture. We're going to be like switching off. It'll be really exciting and fun. So yeah. Yeah, so a couple announcements before we get into animating today. There's a new animation guide under resources. So like we had the ultimate plotting guide. Now we have an animation guide. And so that's a really great reference. It just goes through a bunch of different examples. A lot of your guys' like final projects, you might want to be animating something or like simulating something. So a lot of what we're going to be going over today and this animation guide is going to be really, really helpful for that. As for final projects, you should all be in a final projects group. We sent out a sheet with everyone's like emails and everything like that. If you're having trouble like communicating with your group or you're confused about what group you're in, reach out to us and we'll get you all sorted. And just a reminder that the final project proposals are due Friday, October 22nd. So you still have a bit of time, but just start thinking about that. We're going to want these all to be in LaTeX, which we'll be showing you how to write PDF files in LaTeX on Thursday, so next lecture. So you can start like working on it in a Word document or something. And then later on Thursday, once you know LaTeX, you can start transferring it over. And as for your topics and what your project proposals are about, you can write about a certain thing. And then if you change your mind later, that's totally fine. Like you're not stuck to it. But it's kind of recommended that you stick to the same thing just because it's easier for you, less work for you. But don't feel that you're like stuck to any topic. And then attendance link is coming. Cool. So this lecture today is all about animation. So we know how to plot, but now we're going to make our plots kind of dynamic. And we're going to be saving them as MP4 files. So I'm just going to be showing a couple examples. So this is an erosion animation. So this is basically making a landscape and then using some external file for eroding the landscape. So as you can see, it moves. It looks really cool. It's really pretty. And we're going to show you how to do stuff like this. Another example of something that you could animate. Oh, if it'll change slides. Yeah. Here, this is an infection simulator. So all of these examples are taken from EPS 109, which is Computer Simulations with Jupyter Notebooks. It's a class that Emily and I have both taken, which is really, really cool. It's all about animations and simulations. So these are different examples from that class. So here it's just showing like all these dots are representing people. The orange is infected, black is deceased, and gray is recovered. So it's really cool. You can do a whole wide range of things and animate a ton of different things. Cool. Yeah, so just like you can animate a ton of different things, there's a ton of different ways to animate. So the main one that we're going to be focusing on is Ffmpeg Writer. That's the method that Emily and I are the most familiar with for animating. And so we sent an announcement about downloading the Ffmpeg, like, I don't know, library. Yeah. So you can go ahead and do that. If you haven't done it already, that's totally fine. You can do it later. But just downloading that so you have all the necessary packages in order to make these animations. Another common way of animating is matplotlib.animation.func animation. Emily and I aren't super familiar with animating this way. Again, we're like more familiar with Ffmpeg Writer. But if you want to do that way, that's totally fine. There's a ton of documentation online. We can help you a bit. So you can just Google both of these things. The links to the documentation are on this slide. But yeah, we're going to be focusing on Ffmpeg Writer for writing MP4s. Cool. Off to Emily. Okay, so for kind of the first example that we'll be looking at is how you can animate a sine wave. And so I'm sure we've all, like in homework before, right? We've all plotted sine waves. And so for animating a sine wave, all you need to do is first individually plot all of your different frames and then kind of just use the library to turn it into an animation. So you can see here, if you think about this animation, it's just a series of normal plots that you guys all know how to do. And then you just kind of stitch them together into an animation. Okay, so for using Ffmpeg, the first thing we need to do is import necessary libraries. So at the top, we import our usual matplotlib.pyplot as well as numpy. And then for the animation library, you can import Ffmpeg Writer. And so you can see here how there's a lot of kind of code for just how to make the animation. So if you look at the blue box in the middle, this is just the normal code for how you would plot a sine wave. And so really you guys already know how to do animations. You just need to add kind of this outer loops. Okay, and we'll look at each step more in depth now. And so if you look here, like metadata, this is just optional and just fills in some file information such as the title and the artist. And so none of the metadata is really necessary. This is just for if you want to have more information for when you do like file, get info, this information will show up. So for animating, using Ffmpeg Writer, you want to initialize the writer. This is kind of the thing in the library that actually saves each frame to the MP4 file and actually makes the animation. And then FPS is just frames per second. So it's just the frame rate for your MP4, and all of this documentation is also on Ffmpeg documentation website. So if you forget this, that's fine, but just kind of explaining what all of this means. And then as usual, you just initialize the plot. And this is just a figure where the data will be plotted and saved. Okay, so now we can see if you look back at the code after you initialize the writer, the first line of with writer.saving, it just basically just saves each paused frame in the figure. And so here you have to make sure you have like the indentation, and Python knows what the word with means. Basically, it just means that in this loop, writer.saving exists, and then outside of the loop, you don't use it. And so here you can see we have an F, which is just our number of frames. And so we have a for loop to loop through each frame. And then at each frame, we basically plot our sine function. And so you can see here, since we want the sine function to be changing each time, at each frame loop, we change the sine function slightly. So you can see here how like the I changes it slightly, and we plot the function as normal. Some additional plotting commands that we've added for animation. There's just plot.clf, and this clears the frame. Plot.draw, it draws the plot on the figure. And so you'll need to include these so that your animation updates, and so that each step it'll actually draw it and save the frame. And then plt.pause, it'll pause the current frame for a little bit so that the writer can go and save that frame. And then writer.grabFrame will actually go and save the frame. It's also really important that in the syntax for with writer.saving, The second argument, sinusoidal wave.mp4, will be the name of the file you save. And so it's really important that you include a .mp4 at the end. Otherwise, the file won't know what type of file it should save as, and then you won't be able to open it because it doesn't really know that it's a video. And yeah, and so once you have your MP4 as well, it'll just save in the current directory that you're in. Okay, yeah, so looking back at everything again, you first just initialize your figure normally using plot, axes, and then you can define your function. This is how you would do it using Ffmpeg Animation, which is the other library. We won't go into it as in-depth, but just in case anyone wants to use this method, we kind of have this up so you guys can go look at it later if you're actually trying to work on an animation using this way. But they also follow similar steps of initializing the figure, having some sort of function that'll actually plot and animate it, and then saving the animation. Okay, and then you can also see here, this is the same sine wave, but now just in a 2D, 3D kind of grid. So the data itself is just a 2D matrix with values. And then you can also just have the grid be 3D, so you can have a more 3D looking animation. But this is still just kind of basic sine wave. Yeah, and so for this, similar steps of first importing everything. There's also this additional line, the parentheses matplotlib osx. This basically just allows a pop-up window to pop up when you're making the animation. Since usually if you guys have been doing plots in Jupyter Notebook, the plot will just show up in your terminal. But Jupyter Notebook doesn't really have a way for a whole animation to show up in the kind of output window. And so if you include this matplotlib osx line, it'll create a pop-up where your animation will be. And so here we also included more libraries like Axes 3D and Color Map so that we can use them to plot later. And so here also we have the initialization for the animation writer and the figure for the plot. And so basically for this, it's kind of the same steps of you just need to set up how you would plot the kind of one frame of the 2D matrix, and then you just add the animation on. Yeah, and so here we have steps for initializing the 3D mesh grid using mp.linspace. Here, X and Y are the 2D axes, and the Z axis is like the vertical axis. And so basically the 2D grid is all the locations for the data, and then each value in the matrix is just how high the actual plot should be. Yeah, and don't worry if you guys don't like really understand all the code here. It's more just so you guys can look at the slides later, and when you're trying to make your own 3D animation, you can kind of figure it out from these steps. Okay, and then so for animating the 2D moving sine wave, we have the similar structure with our if statement and the colon and indentation. And then in here, we specify how many frames we want to iterate through. And then for each frame, we plot the 2D sine wave. And so here you can see like the middle of the double for loops, that's just iterating over the 2D matrix and applying the values. So if you're coding something else, you could just put something else in your double for loop. And so after this, you would do similarly to how we saw in the 1D wave, you would clear your figure and then just plot the 2D sine wave as normal. And then you'd also make sure to plt.draw and plt.pause and writer grab frame, which are all just steps for the writer to actually save the frames. Okay, yeah, so general setup for any animation in general. First, you just need to import
your libraries and you set up your metadata writer and the figure. And then you create kind of an outer with statement and for loop that will update the data for the number of frames you want to do. And then in the middle of your code, anything that just plots your data. And then at the very end, the 3 steps of draw, pause, and grab frame to actually save the data and make it all into an MP4. Okay, yeah, does anyone have questions about anything? We'll be doing a demo later, so it'll make a lot more sense.
Cool. Yeah, and here are just some quick tips on animating. Some things to keep in mind is your boundary conditions. So let's say you're like trying to animate like the heat equation, which is like a partial differential equation. You need to keep in mind what your different boundary conditions are. That's just a specific example. As for turning differential equations into code, we talked about SciPy, ODInt, like integration as a way to like solve differential equations. Another way you can do it is like anything that's like dx dt can be turned, we can kind of do it by doing like delta x over delta t. So like taking small steps in x and t to kind of like approximate the derivative, if that makes sense. So that's kind of an easier way if you didn't want to use like scipy.integrate.odeint, but odeint is going to be more precise just because it's meant to do that. Also, Google is your friend. Google's always your friend, but especially for this, especially for animating. I know that when I'm animating, sometimes I'll be running something and I'm like, why is nothing showing up? Or like, why is this plotting weird or not clearing correctly? So you can definitely look up a lot of things, kind of play around with it, and you'll get a feel for how the animation works and everything. And also the animation guide. It goes through a lot of different examples, like animating fractals, animating the heat equation, a bunch of other things that maybe necessarily you aren't going to be animating for your final project, but maybe you could, look at that code and kind of get inspired for what you could use to animate your final projects, if that's what you wanted to do. Yeah, any questions about anything before we go into the demo? I know this is kind of abstract, but cool. Okay. So if you all had a chance to download the animation demo notebook, feel free to open that up. Cool. Is that big enough for the people in the back? Cool. So I'm not really going to be writing any code. I kind of just wanted to share this with you all so you had a work through example of an animation. So this is going to be a planet orbiting a star. So like we saw before, we're just going to be importing the necessary packages, NumPy, Matplotlib, SciPy, SciPy.integrate. We're going to be using SciPy.integrate.odeint in order to solve this differential equation. Yeah, and we're also going to be importing Ffmpeg Writer, which again, you'll need to download from the website that we sent out in the announcement. But if you haven't done that already, that's totally fine. This like retina line here just kind of makes the plot like better resolution. It's not necessary. And then because I'm on a Mac, I'm doing %sign matplotlib OSX. But if you're on Windows, you'd uncomment this line and you'd comment this one out. And then it should also work for Windows. And basically what this line does, like Emily was saying, is it just makes a pop out window. So when you run this and you initialize your writer, you'll see like a big pop out window appear, which is kind of like startling at first. And I know when I first ran it, I was like, what is this? But it basically just makes the animation run in real time while it's writing it, which is really cool to see. So we can run this, it'll just import everything. And then we'll just set up our initial conditions. Oh, yeah.
Mine just has an error. I uncommented the one that's supposed to be for Windows and turned the other one into a comment.
Okay. Yeah, Emily will come help you out. Cool. Yeah.
Once you download it as an Ffmpeg file.
Yeah.
Is it an application file?
It's not an application. It should work fine when you're like running it with Python. You just need to
So you won't get it imported into Python. So for it to upload it.
Huh?
Upload
It should be fine once you have it on your computer.
It's on my computer, yeah. So I'm just wondering, what do I do?
Yeah, you should be able to use it now. Yeah.
What do you mean?
Like when you,
I'm gonna import it.
yeah, yeah,
Oh, I see.
yeah.
But actually,
Mhm.
do I need to stick it in my cloud Python file? So that I can do stuff in there?
I think so. Yeah, yeah, try running it like that, and then if it doesn't work, we can troubleshoot, figure out which ones to do. Yeah, if you're running into some like errors, like downloading FFmpeg or anything like that, we'll try and like end a little bit early, and maybe we can like help people troubleshoot with what individual errors everyone's coming up with. Yeah, so just initializing the like parameters of our system. We're gonna have two objects of interest. The first one being the planet, so MP. I kind of based this off of Earth's mass. So this is like technically, I guess, in units of solar mass. I'm kind of neglecting units here just because the numbers would be really, really ugly. So I kind of came up with these trial and error to make something that looks cool. You could totally plug in things with real units and it worked the same, but I just chose these numbers just for simplicity. MS is the sun's mass, so I just set it to 1. And then I initialized the initial positions. So here there are NumPy arrays. I set my R1, which is like my planet, at 1, 0. And my sun is just defined at the origin, so I set it at 0, 0. Again, there's not really units to this. It's just kind of what I came up with. And then for initial velocities, here our Vx for the planet is 0, and our Vy for the planet is 0.75. And then because our sun is stationary, we're just going to approximate it and say, for the sake of simplicity, that the sun isn't moving, even though we know that the sun is moving, but we're just going to neglect that. We're going to say that it's stationary. So we're going to say that its initial velocity is 0 in both x and y, and we're not going to be updating its velocity. So we're only going to be changing the velocity and the position of the planet. In your homework, you'll actually have a problem where you're going to be animating a binary star system. So in that case, you're going to have to update both of the positions and velocities of both of the objects. But I just wanted to show you the simple example first, and it's going to be really, really similar code in your homework, but just adding in that extra, updating that extra object. So once we have our initial conditions, we're going to be coding in this equation that we know is going to be governing our planet's motion, which is the law of gravitation. So here it's a force, but we're really interested in acceleration, right? Because we want to be changing our velocity and changing our position. So let's see. Yeah, so we're going to be using this equation or this function here, orbit equation. Here, our W is defined as a large array that has both positions and velocities. So here it's defined so that the positions of the planet is defined as the 0 to 2nd elements of this W array. And the velocity of the planet in this W array is the 2 to 4th element. So the reason that we're kind of making this more confusing and making it one array instead of separating velocity and position, just because then we're only updating one array and it's kind of easier to work with, especially if like in your homework, you're updating the positions and velocities of multiple objects. Then we'd have like R2 equals W4:6 and so on and so forth. So the notation's like a little bit confusing, but basically we're just storing our position and velocity vectors in the same array. And we're just keeping track of what elements in the array correspond to what values we're interested in. Does anyone have questions about that? I know that's like kind of confusing. Okay, cool. So this isn't super important for y'all to understand, but basically we are calculating the acceleration due to gravity. And that's defined by this equation here. And then our derivative of position is just v1, right? The derivative of position is just velocity. So our r derivatives is this right here. And our v derivatives is this right here. And then we just want to make it into one array, just like we did up here. And kind of a function that does that in NumPy is concatenate. So what that does is it basically takes these two arrays and makes it into one array. So it would be r derivs and then also v derivs. Yeah, I know this function is a little bit confusing, but hopefully that makes some sense. Yeah, so if we run this, now we've defined our orbit equation that's updating our velocity and our positions and our accelerations, and it's giving us everything that we need in order to animate this orbit. But first we need to solve this differential equation. So first we're going to initialize our writer, or sorry, that's a little bit later. First, we want to package our initial parameters into one array. Like I was saying earlier, how this W parameter is an array of both position and velocity. So we're just going to make an array of position and velocity. And then we're going to flatten that array so we can work with it better. And then we also want to make a like a time span that we want our animation to run over. So in this case, this is something that you would just mess around with to get up with the right value. But here I just chose 5 and 500 points within that, right? Yeah. Yeah, so honestly, I don't really know if this line is necessary. It's yeah, so it's basically taking a 2D array and it's flattening it. The whole like behind the scenes of how this function is working, I'd have to like look at the documentation. But that's exactly right. You're basically taking like a multi-dimensional array and you're flattening it into like a 1D array. And that's kind of just how this function is defined to work with. In practice, you would be coming up with your own function and then animating it. So it's kind of however you want it to work. And then we're running this integration solver. Sorry, this ordinary differential equation solver using scipy.integrate.odeint. So you can look up the documentation for this function, but basically the first input or the first argument is the function that you want to like solve. You plug in your initial parameters, your time span, and then any additional arguments. So in our case, it would be the two different masses because those are our additional arguments for our function. So if we run both these cells, let's see, I think I forgot to run something. Awesome. Okay. So now we have this big array sol or solution that basically gives us all the positions, all the velocities of our planet. And we just want to format it nicely so it's easier to work with. So this is looking at all the columns, and then it's taking the 0th to 2nd, all the rows and the 0th to 2nd columns of this solution array. That's just kind of how the solution array is defined. Yeah. And then initializing the writer, like Emily went over in the slides, initializing the metadata, then the writer. Here I set the frame rate to be, or frames per second to be 50, but this could be 100, 1,000, 20, 10, whatever you want. You can play around with it. It's basically how many frames it will show per second. So if you have a larger value, your animation is going to run even faster. It's going to throw, if you set it to 1,000, it's going to show like 1,000 frames per second, just like really, really fast. So here we have it at 50, which is 50 frames per second. And then we're initializing our figure. This DPI is not really necessary. It's basically like setting, it's another way to set figure size. So if we run this, awesome, we'll get this pop-up window here. And you can just close out of this. It's just initializing the writer and initializing this pop-up window. So now we want to actually save it as an MP4. Something to note is right now we already have all of our data we want to animate. In this loop, we're not like calculating anything new or anything. We already have all of the positions and everything. We just want to loop through our like array of positions and plot each one in a different frame to make it like look like it's changing, and we're like calculating all these different things. But we've already calculated it all. We're just like looping through and like making it look pretty, essentially. So here we're doing this like with loop thing with writer.saving fig, whatever you want your file name to be. In this case, I set it to orbit.mp4. And then we want to loop through all of the elements in our data. So I just said for I in range length time span. First, we want to clear our figure. If you kind of omit this line, then it's going to be kind of like plotted on top of each other. You can try it, but it just doesn't really look great. So you want to make sure you're clearing your figure. And then we want to plot. And we also want to plot a scatter on top of it. So the reason that I include both of these arguments is first, I want to plot the entire tail of the orbit up until its current position. So to do that, I'm going to do AX plot, our like solutions array, all of the elements before until the current time step. So this is going to plot the entire tail of the orbit until where we are right now. So if I just did like our solution : 0, it would plot the entire orbit. But I don't want to plot the entire orbit. I want to like give it the illusion of movement. So I'm going to only plot until the current time step. So it looks like this tail is like following where our planet actually is. So I do that for both X and Y. Here I'm just setting like the color, and I'm making the tail a little bit transparent. This is just like, it's not necessary for the code, just makes it look prettier. That's what this alpha argument does, just makes it more transparent. So alpha of 1 would be like the normal color, and alpha of 0.5 would be 50% more transparent. And then here I actually want to plot the current position of the planet. So in this case, instead of including all of the past time steps until where we are right now, we're just going to be plotting the initial or the current time step. So here, that's just our index I. So does anyone have questions about like the difference between like tail and like current position? So it's just kind of making it look pretty, and you can change this to whatever works best for your animation. Cool. Yeah, and then in this case, because we're not updating the movement of the sun, I'm just going to make this a constant, and the sun is always going to be at 0, 0. So if you were animating more than one thing, you'd like do a similar thing as here, but just with your different positions array. And then here I'm just setting the X and Y limits. So it's like zoomed in and you can see it clearly. And then I'm doing plt.draw, plt.pause. Here I set it to 0.01 seconds. This is also something you can mess around with to see what works best for your animation. And then writer.grabFrame, which actually saves that frame to your MP4 file. So if we run this, we're gonna get something that looks like this. So cool. It looks like it's moving pretty slow, like saving it as an MP4 kind of takes a while. So if you're running it like this and you're like, wow, my animation's really, really slow. Like, why is it taking like 10 minutes to run? If you actually play the actual MP4, it could be like 2 seconds. Like what this is showing, the speed of this is not at all indicative of how long the MP4 is. Yeah, so we'll just let this run. It won't be much longer. So yeah, it's kind of neat. So again, the ax.plot is basically plotting the tail up to where the planet actually is. And then the ax.scatter is just plotting where the planet is. So just that big dot. Yeah. What's that say? Ax.clear? Yeah, let's try it. Okay, just to show you, let's see. Hey, Emily, what directory is this in right now? Or I guess I could just. Okay, yeah, I got it. So now if we open this, let's see, will Jupyter let me play this? Let's see. Okay, I'll just let's just see what it looks like if we don't clear it. I'll save it as something slightly different so we still have the original file. Yeah, that's another thing is if you name your 2 files something that's exactly the same, it won't even ask you, it'll just rewrite that file. So if I were to run this without clearing it, even if I didn't let it run all the way through this like writing loop, it would overwrite the file that I just made. So that's just something to think about. And that's why I'm like changing this file name a little bit so that we can still access our previous file. Let's get rid of ax.clear and let's see what this might look like. Yeah, so here you're not clearing your like ax.scatter, ax.plot. So it just doesn't look as pretty. It still works like, yeah. Yeah, also these pop-up windows are kind of annoying. Like you can't, like if you try and access something else, it'll like pop up in front of it. It's just like really annoying and something to think about. If you're running like a really long animation, you're not going to be able to like do a lot of other things on your computer. Yeah, so that's a little bit different. The only way that I know is to do this pop-up window. I don't think Jupyter Notebook really has a good way for it to run inside the Jupyter Notebook file. But I don't know, you might be able to Google and find something there. But yeah, this is just a way for you to kind of visualize what the animation is looking like. You don't want it to be like running for like 10 minutes and then you look at it and you're like, wow, this is not good. This is not what I wanted at all. So it's kind of cool that you can see it while it's actually writing the MP4 file. But also if you wanted to stop it, you can just hit like this like stop button or interrupt and it'll like kill the animation. It'll still save like as far as it's gotten, right? Because it's saving as you're running it. So then you'll just have kind of like an incomplete MP4 file. Yeah. And then the last thing that I wanted to show you all is the same orbit, the same thing, but instead of plotting the entire tail, kind of having a moving tail. So a tail that's moving with where the planet position is. Kind of weird to explain, but I'll show you what it looks like. Here, why don't I just run it and you can see. So in this case, it looks the same, But once it reaches a certain point, then the tail starts to follow where the planet's going. I just think this looks kind of cool. And as you can see, as it's moving faster, the tail's getting longer, right? Because it's covering more distance in a shorter amount of time. So I just think it's a neat element that if you all wanted to add to your animations, would be a cool thing to include. So let me kill this cell. So how you would do that? Here I just set a tail length. I just chose an arbitrary value of 50, but you could set it to whatever you want. Then here first I'm checking whether my time step is less than my tail length. And if it is, then I'll plot like normal. I'll do the exact same thing. I'll plot all of my previous positions up to the current time step. But if my current time step is greater than my tail length, then I want to plot all of the elements from my current position minus my tail length up to my current position. I feel like that's kind of confusing, but so let's say I'm at time step 60, so I equals 60. Then I would plot all of my past positions from 60 minus tail length, so 10 to 60. So you're kind of like omitting some of the previous positions in order to make this like moving tail kind of look. Does anyone have any questions about that? Cool. Yeah, so we could make this like, I don't know, let's say we wanted our tail to be like, I don't know, does anyone have a number? Anyone? Tail length? 5. Yeah, let's do 5. Let's see what that looks like. Yeah, so here we have like a really, really baby tail. So these are just things you can mess around with, but it's pretty cute. And then if we wanted to like make it like a really, really long tail, we could set like tail equals 100, see what that would look like. Again, yeah, in the beginning, it's looking the exact same because it's the same code. And then once it reaches 100, then it starts to move with it. So this is just a really, really long tail. Yeah, there we go. Yeah. Yeah, and then these MP4 files are just saved in whatever directory you're working in. And you can run them, or you can watch them in like your QuickTime player or whatever you have on your laptop. Yeah, does anyone have any questions about anything I went over? I know that was kind of a lot, but. An error? Okay. Let me stop this. Cool. Yeah, Emily, do you want to do the forest file example or okay? Yeah, so I guess now we could do some like kind of troubleshooting stuff with people individually. That's kind of all we have to show you today. Again, we have the animation guide. This demo's posted, so you can reference that. Again, this is really, really similar to problem 2 on your homework, like really, really similar. So like reference this definitely. It'll make it a lot easier. Yeah, but if you don't have any questions, aren't running into any errors or anything, you're free to go. Yeah. Cool. So if there's not anything, it's not running anything, then you can just like automatically. Not that I know of off the top of my, I'm sure there is, like I'm sure it exists, but I don't know it off the top of my head. Yeah, it should be the right one. Yeah, but if it's not running anything, like not like actively running an animation, you can just like put it in. But if you try and like skip the edit Yeah. What shape? Yeah. Yeah. So if you just
Yeah.
like when you're it's okay if I like
Actually,
yeah, so we have this array here. So we don't want to like access all of this. So this is like
Where do you
part of this.
running from?
Right, so if you think about it, like our position, initial position,
Oh,
initial VX.
that should be closer
But we only want to plot
I don't really, I
our-
don't know how to get this.
So that's why we're kind of indexing it like this, so we're only getting pieces of.
Yeah, they'll be able to help.
Yeah.
Oh, so we're gonna have this here.
Yeah, to like help like,
Yeah, this is something that I think. Do you have Python, like, do you have any clones like Python installed on the computer? Like, are you operating with Python library? Yeah, you're. That's like, this is, I'm not sure. Yeah, it's. Yeah. You all, yeah.
it should be just
I don't know, does it affect things? On or uncommented or commented?
I mean, I don't really know. Yeah. Gotcha. Okay. Yeah, so wait, when you run like import FFmpeg. Sure, you can try that. And let's see what happens.
Yeah, it's indeed. I was reading through it, like you said, yeah, it's like a sativa or. Please stop recording first and foremost. Okay, is there any questions on this? Oh, I think Matthias left, yeah. Okay.
Oh, yeah.